Okay, so notice that from X to B is isothermal. With an isothermal process, heat can flow in. We let the heat flow in. With an adiabatic one, though, heat doesn't flow in, and adiabatic processes cool. That is, when the piston moves away from the gas and no heat flows in, the gas, when it bounces off of that piston moving away from it, comes off at a slower speed. Or another way to think about it is that the heat that flows in, this is zero, right? So if that's zero, and we have definitely a positive amount of work done. If this is positive, that's got to be negative. It's got to get colder, okay? So the way we're going to do this is we're going to use the adiabatic formula to figure out the pressure here. Knowing the pressure, we'll be able to figure out the temperature. Knowing the temperature and the number of moles, we'll be able to figure out the delta U. We already know, by the way, that Q is zero. Okay, that's what adiabatic means, is that heat doesn't flow in or out. It happens quickly or it's well insulated. Okay, so our first step here is to use this guy, PV to the 5/3 equals PV to the 5/3. Okay, so we're going to go from here to here. Okay, so we know 85, 1 e to the minus 3 to the 5/3 equals some pressure we don't know, but we do know this volume here, right? We know it's 5 times 10 to the minus 3rd, and that's to the 5/3. And this is the easy one to solve for. We don't have to take like a 3/5 root or something like that. Okay, so 8e5 times 1e minus 3 raised to the 5 divided by 3, forward arrow, divided by 5 e minus 3 raised to the 5 divided by 3. And what that formula does is, by the way, is it makes the volume more important. Okay, and I get that pressure, the pressure at C is 54719.2 pascals, right? So it goes from 800,000, is that right? Yeah, to 54. So it gets a lot less, right? Which looks about right. You see that? Okay, looks like a little more than half. All right, so now we've got that. Now we can figure out the temperature at that point. Okay, there's lots of ways to find the temperature. We could use the combined gas law, right? So we could use PV over T equals PV over T. But you know what I'm going to do, since we need to know the moles anyway, let's find the moles. Okay, so moles from the ideal gas law is PV over RT. And at this point, we know everything about it, right? We know the pressure, the volume, we know the temperature, right? Okay. We know it's 430 there. So let's go ahead and just use this, okay? So let's go 85. That's our pressure. And then our volume is 1e minus 3. R is still 8.31. And our temperature is 430. So I'm going to figure out the number of moles here. So 8e5 times 1e minus 3 divided by 8.31 divided by 430. And this is like 0.22. We figured this out in the last problem. So the number of moles is 0.22388. Notice it doesn't ask for the number of moles, but we figured it out, right? So now the temperature from the ideal gas law, right, is going to be PV over NR. And this is going to be the temperature at C. So it'll be the pressure at C, the volume at C, and then the moles doesn't change, right? Okay, so let's go ahead and plug that in. The pressure at C, we just figured out, is 54,719.2. The volume at C is 5 times 10 to the minus 3rd divided by NR. So N is 0.22388. And R is still 8.31. Okay, so let me find that number. There it is, that guy, times 5e minus 3 divided by the number of moles that I just got, divided by 8.31. And I get a chilly 147.06 kelvins. That's the temperature at sea. Okay, pretty sure that's what I got. Yeah, there we go. All right, 0.057. All right, so now we want to figure out, let's see, none of these, by the way, are the things that we want to get, right? We can't figure out work unless we can do calculus, right? Because the pressure is ever changing, right? And I actually posted a video on how to find the work for an adiabatic process, but let's assume that we don't want to do calculus right now. Let's use this guy, okay? So delta U is 3/2 nRT. Delta T, sorry. So delta U is 3/2 nR delta T. So it's going to be 3/2 0.22388 times 8.31. Keep everything separated here. And then our change in temperature is that it goes from 430 to 147, right? So it's going to be 147, the final temperature, right? 0.057. Whoops. Eraser. Look at that, huh? Pen. All right, minus 430. Wish there was a simple way to do that, right? Okay, so it's always final minus initial. Of course, you know that this is going to be a negative delta U because the temperature got so cold, right? Okay, so let's do this. 0.3 divided by 2 times the moles that we just got times 8.31 times left parenthesis, that final temperature, minus the initial temperature. And I get that the delta U is negative 789.61 roughly. Okay, so 606, yeah, sure. All right, good enough. All right, so that is our delta U. It gets cold, it loses heat, right? The temperature drops, so it loses internal energy, right? Okay, so now it says, what is the Q? Well, we already know Q is 0, right? So since Q equals delta U plus work, and since we know that it's an adiabatic process, adiabatic means Q equals 0, right? Okay, so that's going to be negative 789.61 plus the work. Therefore, the work has to equal positive 789.61. Crazy, huh? So if you did the integral, if you did the calculus, right, you'd actually get 789.61, right? And therefore the delta U, since no heat flows in to provide energy, the delta U has to be negative whatever the work is. All right, do we answer all the questions? I feel like we did. Let's see, find the work. Yep. Find the Q. So that's how you do it. Okay. Now, if you had calculus, you could figure out the work directly from calculus. And I posted a video about that, but, I don't know, unless you love taking definite integrals, maybe that's not the thing to do. All right.